So, welcome to the second part of this today's lecture. So, here basically we will be using R to implement those models with univariate time series models, that is autoregressive moving average and combination of these two models. That is basically we will try to use the ARIMA model in case of the data which we have taken from the Bombay Stock Exchange, which is the BSE Sensex daily data. So, like the previous classes, here we will be using the R script, and we have created a R project folder by the name of ARIMA R project. So, here we have kept the data file, that is the BSE daily XLS, and the script file ARIMA model.r. So, once we click on that, this will open here. So, from this here we can say the first thing, what are the packages we have used? We have used the packages Read Excel, Forecast, URCA and T-Series. Read Excel, as we have discussed earlier, to basically import the data. Forecast to basically implement the ARIMA model. Then URCA for the unit root, and alternate package for the URCA, that is the T-Series. So, first we have to install the packages if we have not installed. If it is already installed, then we have to only call those packages using the function library in this particular session. So, let us call all these packages here. So, we will keep the cursor here. We can click on the run. So, you can see here nothing error. So, that means it has been successfully called or attached to this particular session. So, let us do for the forecast. So, in the forecast, let us see what we have got. We have got message there is no package called forecast. That means this package has not been installed in this particular system. So, to install that, what we will be using? We will be using the function install packages forecast. So, once we have our cursor is here, we can click run. So, now you can see here what we have, this stop button is appearing. That means now this particular package is being installed. So, once finish, this red button will disappear, and here we will get the downloaded binary package are in this. So, it is basically installed. Now, if we call that forecast package here, so we can say now there is no error. So, let us call another package, that is URCA unit root, then the time series. So, these are the only warnings. There is nothing error in that cases. So, first thing we will import the data. So, we are importing the data using the command read underscore Excel, and this is basically the name of the data we are keeping. Now, here within the code, double code, we have kept the data file name with its extension, that is XLSX. Now, if I are running this here, so what we got? There is no error in the console, you can see. So, that means the data has been successfully imported. Here we can see in the environment pane, now the data and object has been created. So, if you click it here, it will show you there are the two columns we have. Here we have 2472 observations, and there are the two variables we have. Now, let us first check the few observations using the command head. So, here we can write the head and data. So, we can click, and here we have the first 6 observations of this data frame. Let us say if you wanted to see more, so we can write head, then we can write data, and we can write, let us say 10 observations we wanted to see. So, if you see here, now we have the 10 observations. Similarly, we can see the last few observations. So, we can write tell data, let us say last 4 observations we wanted to see. So, if you see here, we have now in the console we have the last 4 observations of this data. So, the last data we have 29th December 2023. Then the next what we have to do, we have to convert this data into the time series. So, to convert that, this is the TS data, the name of the converted data. So, the new data which we are going to create, the name of that data is TS data. Now, how we are converting the existing data, this data frame as in the time series, that using the function TS. Then I am using data, this assessor sign, that is the $sign, the close, that is if you click on here in the data folder, so what we have the two columns. First column we have date, and the second column we have the closing prices of the BSE Sensex. So we are calling it here the closing prices. Now the start date is basically 1st January 2014, and frequency is 252 for the daily data we have kept here. Now if we run here this, so we can see here we have another this object has been created where it is written it is a time series data starting from here 1 to 24 to 72. If you wanted to see that data, so we can see using the command here view. Remember view, in view V is capital, so we can write view and TS data. So here it will be an object. So if we click here, so this is nothing but the data will be time series form here. Now let us say if we use the print TS data command, so what we get. So now if you click on the print, so here you can say it will show you the certain observations. So here we can say is time series data starting from the 1st January 2014 and ending from 2/4/2023. Frequency is 252. So this is the from the first 8 observations are here, and the next 9th onward starts here, then the 17th onwards here. So we have this series up to these observations. Now these are the some preliminary things we have done. We can get the summary of the data also. So let us take the summary of this data. So we can see here the summary of data: first quartile, median, mean, third quartile. Then as we have discussed in a univariate time series ARIMA modeling, we follow the Box-Jenkins process, which basically gave the 3-stage modeling. That is, in the first stage what we call the identification, second stage estimation, and third stage is the nothing but the diagnostic checking. So the first stage here we are discussing, that is the identification of stage, to finding the most probable order values of P, Q and D. So before that, let us transform the data. So transform here we are basically taking the natural logarithm of the time series data and saving it as the LNTS data. That is basically taking the natural logarithm of the data. So if we take the natural logarithm of the data, so we have created here, and again this is nothing but the same time series, only thing we have used now log. So the first thing, let us plot that data. So if you are plotting this data, we are using here the base command plot, then this data frame, that is the TS data. These are the how it will look like. This type is line, color is red, X lab, that is the label of for the X axis, label of the Y axis, and this is the title of the plot. So if we run here, so here you can see this graph appears. If we click on the zoom button here, it appears. So from here we can see this is nothing but the BSE 100, how it has evolved from 2014 to 2023. So over the years, this is the how it fluctuates. If we take the plot of the log of variable, so we can see there the trend or the variance, it is not changing. Only thing, the variability will be little less compared to the. So here we can observe this thing. So by looking this graph, what you can assess, keeping the last class when we have discussed about the stationarity. So one thing what we are getting here, the data has trend. So as the time passes, it is the upward trending. Is the data stationary? No, obviously the data is not stationary. Does the mean is constant? No, the mean is not constant. If the mean is non-zero, yes, the mean will be non-zero. So by looking the graph, we can sense that the data is non-stationary. So to confirm that, that is to find out the value of D, what we will be have another graph, that is the what we call ACF. So if we see the ACF, so here in ACF what we can see, it is decaying very slowly as t moves towards time increases. There is very slow decay in the autocorrelation function, which is again an indicator of non-stationary data. Now, to confirm that, we are using the statistical test, that is the unit root test we are using. So here I am using again the ADF, though in the last class we have discussed the different unit root test, but for this particular class let us limit ourselves to the ADF. So here again the ADF basically from the URCA package we have used, the URDF is the function name. So if we see here now the unit root test, the test statistic value is minus 2.63 and we have to compare those values with the tau 3. If it is more negative, then we'll reject the null. The null is the series is non-stationary. Here since the critical value is not more negative than the tabulated value, so calculated value is not more than the tabulated value, that means we do not reject the null. So we are accepting that the data is non-stationary. So either the graphical analysis or the statistical examination both says that the series is non-stationary. So let us difference that to make it stationary, as we know that for the modeling of we need a stationary series. So here basically we are creating a stationarity series. So this is that we are taking the difference, and the difference data has been stored by the name of ln ts data dot d1. Now let us plot this. So here if you see plot, obviously now it looks a data of stationary nature. So by looking this we can say that it has become a stationary data. Let us also check the ACF. So now if we see the ACF, what we can see here, that after one leg, after the 0 leg, it is almost decaying very fast. So that means the data seems to be a stationary here. So to confirm that again, so we are again performing the unit root. So let us confirm the here. Now if we see here this test statistic is minus 35.159, which is more negative than the tabulated value or the critical value. That means we are rejecting the null. If we are rejecting the null, we may accept the alternate hypothesis. So alternate hypothesis is that the series is stationary. So it confirms that after the differentiation, the series has become stationary. So once the series is stationary, we will now moving to the determination of P and Q. So to determine that PQ, obviously we will take the advantage of the ACF, and so here ACF is basically decaying very slowly. So that means it may follow an AR process. However, what will be the order of AR process, that is difficult to say about looking this. So let us say another, that is the PACF, partial autocorrelation function. We will see for which we will be using the function PACF and the data frame name comma the maximum like for which we wanted to the partial autocorrelation function. Other two commands here are basically for the specification of the graph here. So let us execute this command. So here we have the PACF. So now if you look here the PACF, so after the 1 it almost is 0. Only one non-zero values we have at like 1. So it says that it could be an AR1 process. So let us first fit the model using that the autoregressive part has the 1 and another one for the D, and for MA we are putting 0. So let us run this model. So here what we have, we got this value of the estimated model. However, the probable chance is that we may have the equal model for every other one. So let us say, so that is autoregressive model of ARIMA model of 1 1 1. So again here we are fitting another. So let us see here. So we can compare these two. However, this may be the probable candidate. So the second stage is the estimation. However, there is the, fortunately what we have a function in the forecast model what we call the auto ARIMA, which basically based on the long estimation of the different models, they select the best one. So we will be using this here, this forecast. Then there is the option of trace true, stepwise true. So if you are putting stepwise false, so basically it will take much longer time because they will estimate each models. When we say stepwise true, that means they are doing in the bunch. So let us run this model here, command. So here you can see the what we got, the fitting model using the approximation to speed things up. So basically it will be little more fast compared to the if you and when we are putting stepwise equal to false. So let us say what the final model it gives. However, remember, if you are using the whether stepwise true or false, it may affect your result. So again we can observe here this red button. So if it is there, that means still processing. If it is not there, disappears, that means the final result we have got. So once we get the final result here, that will appear here. The final model is this. So since the data is quite large here, so it may take a few seconds. So you can see, so after this what we have got, here we have got the best estimated model according to this auto fit is the ARIMA 011. That is, it has not taken any leg of AR, neither the leg of MA. It has taken only one, that is for the integrating of T. So let us choose that as a final model here. So I am using that ARIMA, now estimating that particular model, storing the result here, model 1F. So if we execute that and if we take the summary of that, what we get here. See this, the sigma square log likelihood ratio test, AIC, AICC and the BIC information criteria. Then here we can save all this mean square error, root mean square error, mean absolute error, mean percentile error, mean absolute percentage error, mean absolute error and S1. So all these information we will get here. Now, so the third stage now is the diagnostic test. So once we have estimated that model, so and store that model into here model 1F, then we can use that name to basically for the diagnostic test. So here we are asking the command check residuals, or then we are giving the reference of this particular model here. So once we use this, we will get the different plots here. So this is the basically plot of the residuals. By looking the plot of the residuals, we can observe that there might not be the problem of non-stationarity or autocorrelation. Here is the ACF of the result, and here basically that the distribution of that particular residuals we have. So if you look the distribution, it looks like that it is a normal. Here in ACF cases, there seems the problem of autocorrelation here. So to check that, let us say here first thing we are doing, we are storing the residuals of this model in the form of RESA. So this is the estimated result which we are storing into this object. So here you can see that we have that as the time series here. Now we are using the box then test box Q test for the examining the autocorrelation. So here what we can observe, the squared value is this, degree of freedom this, and p value is 2.681 e minus 12. So this is basically what we call the scientific numbers. Here for e minus 2 is basically 10 to the power minus 12. If it is 1, it would have been plus, then it will be 10 to the power 12. So 2.681 multiplied by 10 to the power minus 12. That means it will be very close to 0. Close to 0 means p value is very much closer to 0. So we can assume the value of p is basically equal to 0. So that means we are not accepting the null, we are rejecting the null. Here the null is there is no autocorrelation. So there it seems there is the problem of autocorrelation. So in that case what we should do? In that case basically we can add the lag terms to avoid the autocorrelation problem. So in that case basically we can have the different model. So let us say instead of the AR equal to 0 we can put 1 or 2. But here in this model, especially in ARIMA modeling, we have to do a lot of experiment to find out the one exact model which we will be using for the forecasting. So these are the diagnostic tests based on which we will be basically choosing our best fit model. Then the last, obviously we use this model for the short term forecasting. So how to do the forecast? For the short term forecasting we can use the auto plus forecast, and you can give the model reference here. We can store the data, or we can for example let us say if we are plotting here, so that we can write auto plot function and then we can give forecast model. So if we click on that here, then we can see here this particular graph. So this part is basically forecasting. Here these are the basically standard errors, and this solid line shows the forecasting of the series here. If you wanted to see value, so we can store it. Let us say we are having forecast values and we are storing that here forecast as the function, and we can write model. So we can choose this model, and here, so here we can see the 10 observations of the series had been forecast. So this is the series has been forecasted here. So this is the log ST data, and the values are basically 9.6, 9. So on, so 3. Then in that case we have also mean, everything we will be having here. So we can extract that series. Let us say we can have the forecast data, then we can have this FCV, and we can have the value of this X. So if we run here, then we have this F data. So let us view this F data. So these are the values we have. So that's how we use R to implement those models. So thanks for the class here. In the next classes again we'll be discussing certain theories, then we'll be using again R to implement those models. Hope you are enjoying this course and you will be till the last of this course. Thank you so much.